Okay, and here is the last topic on probability. Binomial and geometric probability. Now, binomial is something that we did cover in class. Geometric was something that we did not cover yet in class. This was right around the time when I got my surgery on my vocal cord. And so I just figured, I'll just show it to them right before the AP test. And it's an easy topic, so I don't think it'll be too difficult for you. And again, you can use your notes on the AP test, so I would just write this stuff down. Okay, binomial, I think, is highly likely to come up on the AP test. I would be surprised if this wasn't on there in some way, but here's the tricky thing. They're probably not going to use the word binomial, so you have to be the one to figure out, this is binomial. And if it is, then great, because you've got a formula and you can use your calculator, and it should theoretically be a pretty easy probability question. So here's what you need to check for if you want to decide if something is binomial. You got to check bins. So, do you have a success or a failure? Is that clear cut? If so, good, you're on your way. We need to have independence. And you kind of have to reason your way through that. Like if we're talking about throwing darts, is each throw independent of the others? Yes. N is we have a fixed number of trials. And then S is the probability of success has to stay constant. If all of those things fit, then we're dealing with a binomial scenario. Now, the new thing is geometric. And geometric looks like binomial except for the N. In this case, there is no fixed number of trials. Okay, so we still have a success and a fail, we still have independence, and we still have a constant probability of success. But we do not have a set number of trials. What's going to happen is we're going to count until the first success. So you're just going to keep going until you get a success. That is the difference between geometric. Binomial, again, would be like maybe we throw 20 darts and we want to find the probability that I get at least 12 bullseyes, let's say, in 20 throws. So that is a fixed number of throws. This would just be, I'm just going to keep throwing until I get a bullseye. Okay, so we're going to run through both of those scenarios a little bit more in detail. We're going to start with binomial. Here's everything you need to know for binomial. These formulas are on the formula sheet, which you can totally use, the one that AP provides for you. Again, it's been posted on our PowerSchool page a ton, or make your own formula sheet. But here are the formulas for mean and standard deviation. Again, it's got to be for binomial. And then this is your general guideline for finding probabilities involving binomial stuff. I'm going to walk you through some examples of both of those. This is a reminder of how to use our calculator. If we're finding probabilities and it's for an exact amount, it's an equal sign, you're going to use binomial PDF. But if you have inequality symbols at all, then it's going to be binomial CDF. And you go menu, statistics, distributions, and then you got to look for binomial. Don't use geometric or Poisson, it's binomial for these. All right, so here's an actual example. So suppose the probability of getting a bullseye playing darts is 0.37. We're going to throw 25 darts and count the number of bullseyes. Each throw is independent. So do you see if I check bins, I do have a success and a fail. A success is a bullseye, and a fail is anything else. It said each throw is independent. N, I have a set number of throws, which was 25. And what is my constant probability of success? The probability of getting a bullseye is 0.37. Now, if they ask you for justification as to whether this is binomial, you would write all of this out beautifully in sentence form, okay? So what I have right here is not great if you're told specifically to justify, okay? Justify would mean write sentences. Sound like a college level student. Okay, so up here, part A, how many bullseyes would we expect to get? So think of expected value, and expected value is a mean. So my little formula says I'm going to do n times p. N is the number of trials, which is 25, and P is the probability of success, which is 0.37. So when I multiply those two together, I'm going to get 9.25. And if they ask me to interpret that, then I would go back, way back to my last video. Right here is how to interpret expected value. So if I repeat throwing darts many, many, many times, I would expect to get 9.25 bullseyes on average per trial. That's how I would, or per throw. I guess I'd be more specific on what a trial is. All right, anyway. B says, what's the probability that we get in the range from 5 to 9 bullseyes inclusive? So if I write that out, I am including 5 and I am including 9, and I'm finding the probability of getting in between those. All right, so this is where we kind of employ this formula right here. So we're going to take the number of trials, choose the amount we want to get. P is the probability of success. That's going to get raised to whatever this bottom number is. 1 minus P is the probability of a failure, and then we're raising that to the n minus x. So if we're succeeding x times, we're failing the other n minus x times. I'll walk you through that. Whoop, went too fast. Okay, so my lower bound is going to be a 5 and my upper bound is going to be a 9. So out of my 25 that I'm throwing, my lowest number of successes is 5. So I'm going to take my probability of success, which was 0.37, and that is going to get raised to the 5th power. Then I'm going to do 1 minus 0.37, which is 0.63, and that's going to get raised to the 25 minus 5. So this is the number of ways I can get 5 successes in 25 throws. This is the probability of getting a bullseye 5 times to the 5th power, and this is failing the other 20 times. Now, I have a range of values, so I also have to account for the fact that I could get 6 successes. 5 is the lowest. The next would be 6 successes, and I repeat this process of raising that to the 6th power, and then my failures would be to the 25 minus 6, which is 19. And I would keep going. After 6 would be 7, then 8, then 9. Now you are allowed, when you're showing your work, you're allowed to skip like that. You have to show the first, you have to show the next, and then you can do plus ... plus the last one. And the last one is getting 9 successes. So if I succeed 9 times, then that would mean that I'm going to fail the other 25 minus 9, which is 16 times. This is the setup you need to show. Now you can go to your calculator though and get your answer. So we're going to go Menu, Probability, Distributions, and you're going to look for binomial. Since this was an inequality, we're going to do CDF. Number of trials is 25. The probability of success was 0.37. My lower bound of successes was 5, and my upper bound is 9. Hit OK, and there's your final answer, 0.528. Okay, what's the probability that we get more than 10 bullseyes? So the probability that I get strictly more than 10. Here's where you have to be careful. The lower bound is not 10. I need to be strictly more than 10. So my lower bound would be 11. But I'm going to structure it the same way. So it'll be 0.37 to the 11th power, 0.63 to the 25 minus 11. And remember, you have to show the first. So this is the first. We have to show the next. So if 11 is the lowest, then 12 would be next. So 0.37 to the 12th, 0.63 to the 25 minus 12. And then I'm running out of room, plus ... plus. And then what would be the highest bound? If I'm going greater than 10, I start at 11, and the highest I can go is 25, because that's all I'm throwing is 25 darts. So it'd be 0.37 to the 25th, and then 0.63 to the 0. All right, and so now I'm going to go to my calculator, and I'm going to type this in. So again, we're going to do Menu, Probability, Distributions, Binomial, CDF. The number of trials is still 25. The probability of success is still 0.37, but this time my lower bound is 11 because I have to be greater than 10, and my upper bound is 25. And I hit OK, and there's my final answer, 0.298. Okay, now the only other kind of problem would be if it's asking for what is the probability. Here, I'll add it in. What is the probability of getting exactly 15 bullseyes? Okay, so then it would be 25, choose 15. It would be 0.37 to the 15th, 0.63 to the 25 minus 15. And then I would go in my calculator, and it would be slightly different this time because it would not be CDF. Because we are looking for an exact value, it would be PDF. So Menu, Probability, Distributions, Binomial, PDF. Number of trials is 25. Probability of success is still 0.37. And my X value, I forgot, what did I say? I said 15. Hit OK, and there's your answer, 0.0107. Okay, so that is binomial in a nutshell. Now here's geometric. So again, with geometric, I already wrote this down, but here's the big thing. There's no set number of trials. We're just going to go until we get our first success. So here's a little example. Barney's making phone calls to get people to go to a laser tag convention this weekend. Historically, there's a 30% chance that he's successful when he calls someone to go. All right, that is our constant probability of success. Was 30%. He is going to call until he gets the first success and find someone to go. Okay, we do have a success or a failure. Either they go with him or they don't. Each call is independent of the other calls. Whatever happens on the first call has no effect on the other calls. But here is what we do not have. We do not have a set number of trials, a set number of calls. It says he's going to call until he gets the first success. So that is an example of geometric. See, it would be very easy on the AP test to start off with a problem that's binomial and then change it slightly into geometric. So here are your formulas for mean and standard deviation if it is geometric. These are on the formula sheet. But if you're making your own, I would write these down. Okay, it's very similar to, let me go back here. If we know it's binomial, I have a formula for mean and standard deviation. Remember when it was like expected value, that's where we used that mean formula. That could come up here with geometric. So you have these formulas. So P is your probability of success. And then here is another formula you can use for geometric, but honestly, you don't really need this. I mean, if you want to write it down, you can. But I just tend to think through these problems. So here's an example. 7% of people have type O negative blood. What's the probability that on a randomly selected day, the first person to arrive to donate with type O negative blood is the 8th person? So a success is having O negative and a fail is not. Each person is independent. I do not have a set number of people. It does not say, oh, 20 people come. It doesn't say anything about a set number of people. But I do have a constant probability of success, 7%. So this is geometric. Okay, now if the probability of having O negative blood is 7%, then what would the probability of not having O negative blood be? That would be 1 minus, I'm going to get rid of this, 1 minus 0.07. So then we would have 0.93. Okay, so if the first person to have O negative blood is the 8th person, that means the first 7 did not have O negative blood. Okay, so imagine the first person comes and the first person does not have O negative. Then the second person does not have O negative. And the third person does not. And the fourth person does not. And the fifth person does not. And the sixth person does not. And the seventh person does not. But the 8th person does. I can multiply all those together. Now this would be the same thing as me doing 0.93 to the 7th power times 0.07. So here's 7 people not having O negative, and here is my 8th person having O negative. And that is using this formula here. You just don't realize it. So this is a fail, 1 minus the success. So 1 minus 0.07 is 0.93. That was the fail to the x minus 1. We were trying to find the probability that our success was on the 8th person. So that means we failed the first 7 and then we got our success. Now we're not raising this to the 8th power because that would imply then that we would have 8 successes in a row. We just have 1 success. It's on the 8th trial, but it's only one success. 7 fails, 1 success. Okay, the next problem says, what's the probability that it takes more than 15 people until we find someone with type O blood? So I don't know when the success happens. I only know that it took more than 15 people. So if it took more than 15 people, that would imply that the first 15 failed. So all I know is that I failed 15 times. I don't know when the success happened. All I know is that there were 15 failures. And that would be your probability that it's going to take more than 15 people until we find someone with O negative blood. Okay, so this is what geometric is like. It's not, I mean, you can reason your way through it. It feels more like a standard probability type question. Okay, here's a similar problem. So bowler likes to go bowling. The probability of him getting a strike is 15%. So the probability of him not getting a strike would be 1 minus 0.15. So the probability of him not getting a strike is 0.85. Keep that in mind. So what's the probability that he gets a strike on his 10th frame? So that means that he failed the first 9 times. So that would be failing, which is 0.85 to the 9th power, and then he gets his success. And that would be 0.034743. What's the probability that it takes him more than 5 frames before he gets a strike? So I don't know when the strike happened. All I know is he failed the first 5 times. So that would be failing to the 5th power. Again, we don't know when the success happened. We just know that he failed the first 5 times. So that's geometric in a nutshell. Here are the formulas, how they appear on the formula sheet. Okay, so you want to find these, or again, copy them down, all right? That is it for binomial and geometric.